Okay, so the Oscars, what's the big deal? Okay, first of all, I have an agenda. That's my joke. So I'll give you just a mercifully quick biograph. Okay, my name's Poul Petersen, CIO for BigML, the I for infrastructure. Okay, so if you want to geek out about computers and stuff like that, I'm your guy. Does anybody here know what BigML is? You guys familiar at all? I'm not going to go into a long contrived detail. That was just for my own personal benefit. I wanted to know. Just curious. So I have a background in mathematics, physics, and engineering. I had a hard time choosing, apparently. And I love computers and teaching. Those are my fields. So what I'm going to do is I'm going to talk about predicting the winning movies of the Oscars for 2018. I'm going to show you what we did, why this is possible at all, exactly how we did it, okay, short of actually demoing, and showing how this is a blueprint for applying machine learning to whatever problem you want to solve. And I quoted anything because you can't really solve anything, but it's close. And some fun extra stuff if we don't run out of time. Okay, so predicting the Oscars. So on March 1st, 2018, that's before the Oscar winners were announced, we posted this blog post where we predicted 6 categories. So we predicted the winners for, it's a little hard to read on screen, but Best Picture, Best Director, Best Actress, Best Actor, Best Supporting Actress, and Best Supporting Actor. All right? And a few days later, on Sunday evening, the winners were announced. So how did we do? Well, there you go. We got 6 out of 6 right. Okay, it's a pretty good track record. We actually got 8 out of 8. Okay, but there were 2 that the probability was a little too low. We didn't feel like we could publish it. You know, we wanted to have a 6 out of 6 instead of a 7 out of 8. But we actually got 8 out of 8. The 2 that we actually also got right were adapted screenplay and original screenplay. So we nailed those 2. Now this created a lot of excitement, as you can imagine. People have a very short attention span on the internet, so there's a lot of tweeting that went on. So yay, machine learning. I love some of these. Okay, there's no doubt that as I skim the Oscars, you know, nailed the prediction game. I like this one too. Power of machine learning confirmed, because we had to predict the Oscars before people knew machine learning was cool, right? Okay, what if there was a way, wait, we did it, okay. And then there was this one too, which actually I'm going to spend just a minute derailing you on. Oops, I didn't let you read it, did I? That's okay. So this guy was saying, well, wait, if that's true, why can't we predict lottery numbers? We have winning history data available online. Okay? But if you think about it from it's actually kind of a valid question, right? I mean, people think of the Oscars as being this random thing. So let's break it down a little bit. Contrapositive time. Okay, what are we talking about here? So his assertion is that if we can predict the Oscars, we can predict lottery numbers. Okay, you know, you can flip that around. You can say, well, we can't predict lottery numbers, then we can't predict the Oscars. That would be the result of his assertion if he is proved true, correct? Okay, now we know we can't predict lottery numbers because otherwise there'd be this one team out there with some really cool machine learning algorithm and they'd be billionaires by now. So they'd be predicting them all. So we know that this is some kind of a contradiction. Okay, so you can't predict lottery numbers. I'm sure you know this. So there's 2 main problems here why this isn't going to work. First of all, the motion in these typical machines is chaotic. If you don't know what chaos means, it's just extremely nonlinear. All right, so little tiny changes in the initial conditions greatly change the outcome. All right, the ball moves over a billionth of an inch and it's a totally different number. Okay, and you can't measure the initial conditions with infinite precision anyways. Thanks, Heisenberg. Okay, so why can we predict the Oscars? Why are they so different? Well, let's think about it for a minute. How do you actually win an Oscar? Well, there's this voting body, the Academy. It's over 7,000 members, and they vote. And then there's one of the categories is chosen. Okay, so don't we have the same problem as the lottery with predicting intention? Aren't people's brains like some kind of a computer that if you knew the exact state, you can figure out exactly what they're going to vote? And that would be impossible, right? Well, what if we build movie-watching robots? I know somebody out there is thinking about this. This is how we'll do it. So we'll program robots to record audio and video. Okay, there's the Mystery Science Theater 3000, if you don't know that reference. We'll train them to react like a human to the movie. Okay, we'll train these big neural networks, and then we'll run a simulation and collect votes. You'll do like an AlphaZero here. Okay, we'll just run movie. Okay, please don't try to solve everything with AI and machine learning. This is the totally wrong approach. That's a big hammer that isn't even driving a nail in this case. So, if you haven't ever thought about evaluating your machine learning approaches, here's a nice little chart to do it. So on the y-axis there, we have increasing data availability or decreasing complexity. All right, and on the bottom you have the ROI, the impact and cost. Okay, anything down in that corner is a no-go. Okay, the data is either just not available or the problem is super complex and the ROI is close to 0, so you just don't bother in that space. Anything up there, maybe the data becomes available or it gets easier later. So you postpone that problem, hope you can solve it again. Okay, something over here has a high ROI, it's very interesting, but the data is not available, it's complex. That's something you got to think about. Maybe you can do it still. And then in the upper corner there, that's the sweet spot, right? Things that are going to benefit your business, and you've already got all the data, it's just sitting there, and all you got to do is throw some machine learning at it. No-brainers. Okay, the movie Watching Robots is down there somewhere. Okay, I gave it a little bump in ROI because if you actually manage to make a movie watching a robot, it's probably going to be useful for something else. Okay, watching movies would be the last thing it does. Okay, so what if we just guess? Let's just try guessing. So we got 1 of 9 for best picture, 1 of 5, 1 of 5, 1 of 5, 1 of 5. Okay, that's not going to work either, right? Too many combinations. Okay, so why is this going to work? Let's think about coins for a minute. This will make sense, I promise. So we'll take our coin, okay, we'll flip it, and we get tails, we'll flip it again, maybe we'll get heads, and we flip it a bunch more times, right? Okay, so after observing these first 5 flips, what is the probability that flip 6 is heads? You guys didn't know this would be a math class, did you? I'm sorry. Hopefully nobody's having a heart attack. What's the probability that that last is a heads? It's a half, yeah, it's 50%, exactly. Okay, as I stated the problem, I was very careful when I wrote it. These events are independent, okay? So the previous flips don't matter, all right? They don't matter. With one caveat. What if it wasn't a fair coin? There's a lot of tails there, and this is what humans do. They're like, you know, there's a lot of tails. There's 3 and 4. It only was head 1. What if your coin is cheating? Then the probability is low. Okay? Well, but this actually gets us onto the idea here. The movies are not equally likely to be best picture. They don't all have equal probability. So how do we know? Well, we could look at other wins, right? We could say, okay, The Shape of Water wins a BAFTA award, and then it wins a Golden Globe, and then it wins the Directors Guild. It doesn't win the Writers Guild, that's okay, but it also wins the London Critics. Yeah, notice the reference there. And then will win the Oscar. Okay, well, these events are not independent. Okay, these are not coin tosses. They're similar but not identical factors that contribute to each one of these wins. The quality of the acting, the quality of the writing, whether or not you rub elbows with all these same people and they're like, hey, you got to vote for it because you know my cousin worked on this movie. Who knows? There's a billion factors that are all going to correlate these. So we can expect a higher probability for Shape of Water to win the Oscar. That's the basic idea. Okay, so where do we start? So we have step 1, let's predict the Oscars, and step finish is here are the predicted winners. People like to think about this. This is basically all the further tweets go. Yay, we can predict cancer. Nobody ever tells you how hard it was, okay, or how many failed neural networks they built. So what is even step 2? How do you get there? And it doesn't, it doesn't have to be the Oscars. It could be, hey, let's predict some customer churn. Here are the customers we predict will leave our service. What do you do tomorrow? Okay, so the first thing is to state this problem as a machine learning task. All right, so what does that mean? Well, you got to be specific. Okay, let's predict the Oscars. No. No. Let's predict the Oscars by correlating a series of award wins with the final Oscar win. Yes. Okay, that's very specific. Now you know exactly what you're going to do. Okay, this often requires iteration. It takes a little bit of playing. I know I've been working with the pre-series model for the battle, and I went through many iterations. Okay, typically this is about 10% of your overall effort in this project. It's not too bad, but it can be involved depending on how hard it is to describe the problem. Then you got to do some data wrangling. What's that? Does it involve a horse? No. So where are you going to get your data from? How bad is the data? It's going to be full of errors and typos and bad fields and all kinds of data is horrible. Can you access it with an API because you don't want fresh data and you don't want to have to do, type it all in again by hand? Then you're going to have to do some transformations. Okay, your machine learning data needs to be rows and columns, unless of course it isn't, right? You could imagine images or audio files or some other things. But for the majority of problems, it's just going to be some rows and columns, and every row is an instance of something you're trying to learn something about, like a movie. Okay, and it needs to be denormalized, right? One big fat table. So there tends to be lots of nasty work to do in there. And so, in fact, actually, this is the data that we harvested from the IMDb. I hope that doesn't violate the terms of agreement. I didn't actually check. So we have things like about the movie, like the year and the rating, the genre, even the gross and the release date and all that kind of stuff. And then there's data about all the different awards that they've won. And then there's the objective fields over there, which are all the different categories of Oscars that we're interested in predicting. Okay, not too bad so far. So then there's going to be a little bit of feature engineering. You knew that was coming, right? So machine learning is sensitive to good features. Sometimes you give it a slightly different way to look at the data, and then suddenly it finds all the patterns and works perfectly. It might need better features. It might need even completely new ones. And that the whole block there, those three things are about 80% of the entire project. Pain. Pain, pain, pain. Now, I will tell you that because there's pain there's, of course, market opportunity. And so I assure you that BigML is bringing something cool into that 80% effort. Watch for it. It's going to be cool. OK, so predicting the Oscars. Now, this data set that we built, okay, with that 80% pain, is actually available. There's the URL right there. There's a gallery you can go out to. You can clone it. You can play with it a lot as well. So you don't have to do the 80% work if you want to play with this data set. I did it for you. OK, so finally the machine learning part, which is easy. Right, what algorithm we're going to use. Okay, now I'm going to give you a little algorithm selection guideline. This is my personal preference. Okay, so we have on two axes, I just like doing these graphs, I guess. So as we go down on the x-axis there, we have decreasing interpretability, but better representational power, and we pay for it in longer training times. Okay, and in the y-axis, we have increasing data size or maybe complexity. Okay, more complicated data or bigger data. Okay, we're going to break this graph up into three stages. We have the early stage. We're doing what we call rapid prototyping, and mid-stage, or like a proven application, something we know is going to work, and late-stage critical performance. And the idea is that when you're in this rapid prototyping, you don't even know if you're going to be able to predict the Oscars. You have no idea if it's going to work. It could fail. Okay, so you're not going to whip out a deep neural network to do that stage, because it's hard to interpret, right? That graph down there, decreasing interpretability. So you start with something like a logistic regression, just a single decision tree, because they're very easy to understand what it's doing, how it's making its decisions, super easy to interpret. Once you can see that there's actually some signal in there that you're learning from, then you move up to this mid-stage where you start looking at decision forests or random decision forests. Still somewhat easy to interpret, much more powerful, and often you can actually just stop there. But sometimes you have a critical performance, like predicting cancer, and so now I might move to a boosted tree with a really small learning rate, or you might pull out a deep neural network and do that. Okay, also, again, depending on your data size or complexity. Okay? A couple pictures there. Okay, so modeling evaluations. I put those together, so what about evaluations? So all models are wrong, but some are useful. Keep that in mind. They're never 100%. Okay, so we have our data set for these movies, 119 variables, and it's actually from 2016. No, that's right. And the first thing we're going to do is we're going to split it. So we're going to make one data set that's 2000 to 2012, and we're going to train a deep neural network, actually, using all the movies from 2000 to 2012. And then we're going to pipe the 2013 through 2016 movies through there and see whether or not it predicts the right winners for the Oscars. Okay, so we do a little 4-year test. All right, we actually did do this. And for all the award categories, we retained an ROC, AUC, of over 0.98. Okay, so it's very, very successful, which means that the models were able to predict these winners for 4 consecutive years with very few errors. And that actually is the confusion matrix there, which you probably can't quite read. But trust me, it looks really good. Okay, it's quite good. Okay, so modeling evaluations. Now we're going to go to predictions. Don't forget to retrain with all the data, right? We split to see how it was doing, but now we're going to predict for real. We want to predict this year's winners, so you got to go back and use the whole data set. And then we're going to use the whole data set to make predictions. So here we go. We're going to build a model per objective. We'll create a prediction for each candidate. So we take our full data set, we run it through and build a nice deep neural network. Then we take the movie for this year, feed it in there. It tells us if it's going to win and what probability it's going to win. And then we choose the highest probability. Piece of cake. Okay, so how did we do? Well, best picture, we predicted The Shape of Water with so each one of these probability scores, they don't add up to 1, okay? They're individual movies. But you can see how much the model preferred this movie over the others. Okay, the next closest score was a 68. The Shape of Water for Best Director, Guillermo del Toro. The 75 there, pretty much trounced everybody. 99 is definitely a solid win. 88, solid win. 64, so we feel pretty good about these. They're all very solid and correct. Okay? Now, wait a minute. I put the modeling, evaluations, and predictions all at 5% effort, right? How can you have 5% effort for a deep neural network? Those are hard, right? You guys work with neural networks at all? Yeah, are they hard? Can your mom do it? Yeah. Okay, let me just, I'm going to switch to blue because this is deep, okay? Sorry about that. So I'll just give you super brief, very quick overview. Right, so you've got some inputs there, you've got some classes up there that we're trying to predict. Deep neural network is going to have some magic hidden layer, could have more than one, of course. And there's some activation function that takes all the input features, predicts the H nodes there, and then they're all summed together with some other activation function, perhaps, to compute the output nodes. I'm going very fast, I know. Okay, and then the game is that we call these hidden features. And now the game is that we say, well, we can change the activation function, we can add a whole bunch more layers. Each one of those layers can have a bunch more nodes. This turns into a big quagmire of possibilities. Right, you have 8,000 layers and 2,000 nodes or whatever. Right? So what do you do? Okay, well, the problem is that the success is dependent on getting the right structure. If you choose the wrong structure, it's not like it's just like mostly good. It's usually like really bad until you get the right structure, and then it's really fantastic. Okay, so there's not a lot of room for error on this. And there are just too many parameters to be that right. So, and setting them correctly takes expert knowledge. Okay, so the solution, there's two things that we do for you. One is meta learning. So we start with a good initial guess, and the other is we do a network search. All right, so that's the expression, right? We trained 300,000 models, so you don't have to. But basically, we took a bunch of different data sets, we trained a whole bunch of neural networks, figure out which one's the right one, the best ones, and then the optimal structure. And then we trained a model, which when you give it a new data set, it looks at the structure of the data set and predicts the ideal structure. Meta learning. We just used machine learning again. Okay, so we can use this directly or as a seed for more intensive network search. So how does that work? Well, we take our seed and we just try. We go, okay, well, that one gets a score of 0.75, that one's a 0.48. We just build a bunch of these network structures, and then we use a little Bayesian parameter optimization, and we can get an even better network structure. And actually what we do is we create, I think by default, 128, and then we do a little bit of stacking as well. So the neural networks all kind of work together. Okay, and the result of all this is that if you just take an off-the-shelf algorithm across a wide variety of data sets, and so you got all kinds of things here like gradient boosting and naive Bayes and add a boost and k-nearest neighbors and stuff. So the deep neural networks are over there. But that's just for a one-click network search, no configuration, push a button, get a neural network, and it beats everything. And that was what we wanted to do. Okay, so that's how that can be a 5% effort. Now I went pretty fast. So I want to come back to the unfair coin, because this is another little fun side note. So what if you knew that you had a fair coin? This is bonus material, sorry. And you wanted to see if another coin was fair. Well, one thing you could do is actually just flip them a bunch of times. And I have this great picture. I have a 7-year-old son. I set him flipping a coin and recording it, and I have a whole table, and then I played with the data set. So I did this for real. And then you just label them. You say, okay, well, this coin was fair, and this other coin is the one I'm testing. All right, that's the idea. Oh, it says label the fair and unknown. You might have to do a little feature engineering there. I left a little room. You might need a number of heads, a number of tails to make this work perfectly. But the idea is you build a model to predict whether it's fair or test, and we expect this model to fail. Okay, if they're both fair coins, it shouldn't be able to tell them apart. That's the idea. If it can tell them apart, then the new coin is not fair. Does that make sense? Yeah? If these distributions are significantly different, it'll tell them apart, and then the coins aren't both fair. Now, this is something called covariate shift, which you can also use for knowing when you need to retrain your models. Okay? So you can actually take your data set that you've trained and the data set of all the predictions you're making, combine them together, and you can look for when the input data is shifting away from your training data. Okay. Anyways, bonus material, my apologies. So that was the Oscars. At rapid speed. You said 20
Thanks
minutes.
very much. Yeah, it's perfect. It's exactly 20 minutes. That's what I was expecting. I've predicted that it would take 20 minutes, right? So, any questions for the guy with the company that can predict Oscars and maybe some other things in the future, right? No? Oh, you again. But now you get it right quick. I got bashed before, right?
Can you tell us a bit more about the what are the features that you use for the prediction? The 100 and I don't remember.
Yeah.
20, and how many samples? Because there is this expectation that deep neural nets are not competitive if you don't have that many training samples.
Yeah, that's a lie.
Yeah. Okay.
Yeah. No, it depends on the data. So this data set, I forget, it has 119 features and 1,000 some odd rows. I lost it. Yeah, I think it was 1,200 rows, I think, and 119 features. So the features is each row is a movie, and it has all the metadata about the movie, the release date, the gross, the rating, is it PG-13 or whatever, and then it has all of the awards that it's won, like all the examples I showed, like the BAFTA and the London Critics Circle and all the rest of those. It's all in there, and then there's a final. Actually, I'll just show it to you. So. If you go out to the gallery and hit data sets here, on the footer there, and scroll down a little bit, it should show up pretty quick. There it is, movies 2017, and you can just grab this out of here. And now you can play with this too. And so I'll make this a little bigger. And now you can see, okay, here's the Oscars. So those are all the Oscar Best Picture won. Each movie marked no, it didn't win, or yes, it did win, for example. And then there's, the BAFTAs are all in here. BAFTA won, and the categories is actually in items because it comes as a list. The categories that it won, they do theirs a little differently, but you support these lists of items. And I think there's, release date, gross, et cetera. Yeah, so it's 1,159 rows. Yep.
Any other questions? No? Oh yeah, there we got. Why are you so shy, guys? Nothing is happening.
Yeah, so you have a wonderful example for prediction. Do you also do algorithms that can generate things, like can be images or whatever, with generative algorithm like autoencoder or GANs or whatever?
For the neural networks. Yeah, so for the neural networks, we actually just recently released the Deepnets feature, and it's only for classification and regression right now. But we are bringing image analysis as well. So that'll be soon. Yeah, but specifically what you're asking for, no, not yet. Yep.
Any other question? I have one.
Sure.
Out of this 80% work that you mentioned, right? What is, can you give us a hint into the future? What is the lesson learned out of this work that might help the audience, the other practitioners to apply, similar predictions on other, maybe more relevant, right? Applications or use cases.
So it's interesting because even until recently, there weren't even a lot of books about how to do, denormalization for machine learning, right? And there are a few now, but it's always been kind of a black art. Especially creating features or knowing what features you might want to create. And I teach a class where I have a bunch of examples, but they won't make sense speaking them out loud. They're a little easier to show. But a lot of that, some of it is repeatable and reusable, and it's an area of active research. There's been some papers recently on deep feature synthesis, right? And so there's a lot of stuff going on actively that will make that much easier, that aspect, at least bring that 80% down a little bit. I certainly, at least in my mind, having played with it, or having spoken to Ken about what he's working on, because I haven't seen it yet, there's still a lot to be done. It's not going to be perfect, but it makes it better. Yeah, much easier. Let's get it down to 40%, let's say.
Okay.
Yeah.
Cool. Oh, one more question.
Yeah, regarding the search through possible architecture, until you find the best one. Do you just apply a grid search, or do you have any kind of Bayes optimization or any kind of
That's exactly it. It's a Bayesian search. Yep.
Cool. Then Paul, thanks very much. Yep. Give him a hand, and hope to see you again at 3 p.m. for the next session. Thank you.